the participants. Yes.
Okay, now the participants are coming in. Great. Okay, so everybody was in the waiting room, and now people are coming in. So the numbers are increasing very quickly. Great. It's still exciting. Also, I'm doing this now for the fourth time. It's still like it feels like something exciting to be here in this room and at the same time broadcasting.
Hello. Hi, I'm the moderator for this session.
Hi, great to see you.
Are you willing to be recorded for this session because it's automatically recorded?
I'm not sure if I understood it.
So this session is automatically being recorded. So
okay, yeah.
Oh, okay. If you don't want to be recorded, I can stop it.
No, I think it's great. So Wes, if it's okay for you.
Oh, yes, of course.
Thank you.
Yeah, thank you so much. So I still see people streaming in. So I would suggest we start the moment the numbers kind of reach a stable state, and we are not yet there. Yeah, so I think so. We are going online. Okay. So welcome to this third foundation lecture at the 2021 ISBA World Meeting. Due to rather unexpected circumstances, Sonia Petrone was not able to chair this session and asked me to step in. So Sonia told me she would have been honored to introduce a maestro like Wes Johnson, and I'm very delighted that this honor now is mine. So Wes is a professor emeritus at the Department of Statistics at the University of California in Irvine. And being relieved of his teaching duty, he's now on an infinite sabbatical and has all the freedom to continue his amazing research work that he has been doing for such a long time. Wes has contributed to so many areas of statistics that it's impossible to give a full account in 2 minutes. So let me just mention 2 areas. He has worked a lot in statistics and epidemiology, and just has finished a book together with co-authors entitled Introduction to Bayesian Biostatistics. And from the many fields where he contributed, I picked the area of Bayesian predictive methods for regression models for a very personal reason. So when I started as a PhD student in the early 80s, there was a lot of discussion about robustness, influential outliers, all from a frequentist viewpoint. And in these early days of my PhD, I started to read Bayesian papers. And one of the first papers I came across was your paper together with Simon Geiser in JASA on how to use predictive Bayesian analysis to outliers and to inferential observations. And it was one of those papers that really kind of gave me the feeling, wow, this is exactly the way one should do it. So it was one of those papers that made me want to be a Bayesian. So thank you very much. So as I was saying, Wes contributed, and let me just mention a few areas: Bayesian non-parametric survival models, longitudinal data, and many, many others. And as any maestro, along the way, he has gained a lot of insights how to do Bayesian inference in applied problems, how to do it in a proper manner. And it's a great pleasure and honor for us that today you're going to share with us all your wisdom that you gained along the way regarding how to choose priors, and that you're going to share with us some stories about prior choices. So thank you so much, Wes, and the floor is yours.
Thank you, Sylvia. That was a great introduction. the best I think I've ever had. So I really thank you. And it's an honor that that you had read my paper way back then. So, or whenever it was, that was one of my favorite papers. And I'm just trying to remember how to sign in here.
Yeah.
Can you hear me?
We can hear you. We can see the slides. Yeah.
Okay. Okay. And it's also a great honor to have been invited to do this. Alicia said yesterday, the honor of a lifetime, and that kind of stuck with me. It's true for me too. So one of my favorite things to do is one of my favorite things is to have somebody come to me and say, how would a Bayesian do this? And then a big part of that is figuring out how to put real prior information into a statistical model. And with friends, I kind of developed a method that I'm very happy with, that involves working with substantive collaborators in a big way. But let me start with a quote from Dennis Lindley, and I'm just going to let you read the quote because I'll probably botch the reading of it, and then I'll say something after you've had a chance. So Dennis Lindley visited UC Davis, where I used to be. We invited him as a special lecturer for a quarter. And he gave a series of lectures on the foundations of probability, and of course, mainly Bayesian version of all that. So, and he really made an imprint on me. And so at that point, I'd been working as a Bayesian. My thesis was Bayesian, and my advisor was Bayesian, and I loved all of it, but I didn't probably really become a Bayesian until Dennis Lindley visited, and he had a firm impact on me. So anyway, so that was the beginning of me becoming what I call a real Bayesian, as opposed to a pragmatic one. So a bunch of comments here from me. A prior, to my mind, is a misnomer, although I'll use the word throughout this talk. So in our book, we call them knowledge distributions. What really matters is whether the prior information or the knowledge distribution is independent of the data. So, all priors are informative in some sense. So I would have some difficulty with the word non-informative prior. So, but anyway, starting with Brad Efron, who I was having a nice conversation with, he not being a full Bayesian, but he said there is no such thing as a real, as a non-informative prior. And then on Monday, Zhao Li said that it's impossible to construct a true ignorance prior. So I was really happy to hear him say that. It kind of coincides with the way I've been thinking forever about this. So priors can easily be disinformative, even though the intention, of course, is to be benign. So I think the first example I think of for that is putting a uniform prior on the prevalence of HIV in the United States, which would be saying that it's equally likely to be above a half or below a half, which is, I like to use the word silly. So now I know that the prior can go away with big data and so on. But anyway, I still like to think of the prior as having some physical meaning in the problems that I work on. And I've worked on issues related to HIV and diagnostic testing for a long time. No such thing as having a wrong prior, it's your prior. I'm quoting all kinds of other people. I know everybody, anyway, there's a long path of people saying a lot of the things that I'm saying. So it's not like I invented these things, but your prior can be misinformed, but it's not wrong if it's your prior. So scientists having differing priors is a normal thing. And it kind of is what science is all about, is that you start out with differing opinions or beliefs about something scientific, and you hopefully come together and agree with one another ultimately if you are able to observe enough data of the right kind that would be convincing in the end. So the idea is to have your posteriors become similar or the same after observing enough appropriate data. So for me, I was involved with a student in the early part of my career who asked me to be her statistics advisor, and she impressed upon me the importance of the biology and the situations I was in. Before that, I had really just been doing statistics without understanding everything that was involved in the collection of the data and so on. So she actually had me out there in the field in Central California, watching her take blood from cows, and so then we'd go back into the where she worked, and we'd be looking at computer output and so on, analyzing those data. So anyway, so this collaborative effort has been a huge thing in my career. It's really made me whole, I think, as a statistician. And that's where priors come from, is from having interactions with people that know the biology. So anyway, so failing in that, I find Google to be very helpful. If I don't know anything and I'm, for whatever reason, I'm analyzing a data set and I'd like to input some kind of substantive prior information. I put Google in quotes because when Joe Garthwaite and I were first working together on diagnostic testing problems, he went to the library and dug out lots of information that we needed that was very helpful relative to the problem we were working on, data-based priors that were independent of the data that we were actually analyzing. So that made a big impression on me. So overly diffuse priors can be very bad, even if they're proper, and I'll give a good example of this coming up in a minute. Improper priors can lead to improper posteriors, everybody knows, and sometimes people get caught short with an improper prior that has an improper posterior. Not something I want to do, but anyway, I'll use one later on, so I'm not immune to using those. Diffuse priors on model parameters should be calibrated by inducing distributions on scientifically relevant parameters to see if they are reasonable or nonsensical. So I'll make a big emphasis on this. And I've just found the scientists that I worked with over the years, and I've worked with many, they always appreciated this aspect of the collaboration. And we actually had fun in sessions where we were, between us, we were eliciting prior information. I was eliciting from him prior information that he or she was comfortable with, and then together we would come up with a prior that they were comfortable with. So there's a lot of references on this. Everybody has their own priors. There's as many paper priors as there are papers, probably. So a key reference, historical reference, not that far back in the past, is this Garthwaite, Kadane and O'Hagan paper. And it has 140 plus references up to the time. So this is, they're into eliciting, sitting down with a client and turning their information into a probability distribution that's consistent, so that it's easy to imagine, sitting down with somebody 2 days in a row and getting two different prior distributions. And so a major goal is to avoid that, to make sure that there's internal consistency. So some of the references that I've highlighted or that I've listed below are in the Garthwaite paper. And I pulled them out because I remember them from over the years, from running into them for one reason or another. The de Groot paper stands out particularly for me, even though I didn't see it in 1974. I was just in my first year of graduate school, but anyway, I ran across it a little bit later, but not a lot later. So anyway, I recommend these papers for anybody that's interested in getting in on the ground floor of this kind of stuff. And the O'Hagan paper looks particularly relevant. This is going through a real situation. Okay, so anyway, then I can't leave out objective Bayesians. Priors, Berger and others have been, working on these for many years now. And there's obviously, it's obviously impossible to provide a subjective prior if you've got 50 parameters or 1,000 parameters. So there's a real need for priors that can cope and have good properties in those kinds of situations. So in Jim's paper, he points out times not to be subjective. I noted that. But for me, this talks about me, I guess, and my experience with priors, and mine is for this collaborative type of situation and not all situations fall into that category. Okay, so then there's the power priors of Ibrahim and Chen. Have had they have a real presence today. I put in Ibrahim and Laud because they take the predictive approach to selecting priors, which is, the right way to go. Think about things that, you could actually observe down the road, as opposed to regression coefficients. And then there's the paper with my friends Ed Bedrick and Ron Christensen from 1996, a long time ago now. But anyway, that's pretty much the approach that I will be taking throughout this talk. So in the process of writing these two books, I had to think hard about how I would put priors on things that I'd never had to do before. And so it was actually a lot of fun. And in the latter book with Gary Rosner and Prakash Laud, there's a whole chapter on priors in addition to all the priors that come up in the other chapters. So anyway, so if you want to know more about what I'm talking about, those are good places to go. All right, so my first example, O-ring data this is from 1986, is when the Challenger exploded. These are space shuttle launches. And looking at O-ring data, that is to say, was there at least one O-ring failure on a launch? And there were 23 pre-Challenger launches. And Richard Feynman famously was in a Senate hearing or some kind of a hearing in Congress anyway, and they're talking about the issues related to the explosion of the Challenger, and he put an O-ring in a glass of ice water and noticed that it cracked in front of everybody. So anyway, so it's clear that this is not a good thing if you're sending somebody up into space when O-rings are holding the space shuttle together. So, okay, so the data this is a well-known data set from way back there. There's lots of papers on it, and more definitive than anything I'll be talking about here. But the data are binary. You observe whether there's at least one O-ring failure on the date of launch, and you observe the temperature. And obviously temperature seems to be related to whether O-rings are going to fail. Okay, so here's the data. So at high temperatures, there's lots of launches where there's no O-ring failures, but there's a couple where there are, and then with lower temperatures, there seems to be relatively more. Okay, so the standard kind of model for this would be, it's not what they used at the time as far as I understand. They fit a linear regression to the data and decided there was no problem. So the indicator of at least one O-ring failure is Bernoulli. We've got a logistic response, logistic model for the probability of at least one O-ring failure. That leads to an expit probability there. And I'm going to start out being interested in a couple of probabilities: the probability of at least one O-ring failure at 55 degrees and the probability of at least one O-ring failure at 75 degrees. So now these are things that I can think about. So, but at the, once upon a time, priors of the following type were placed on regression, logistic regression models where you have a normal distribution for the regression coefficients and a huge variance. But okay, so well, here's the induced distribution by simulation on the probability of at least one O-ring failure at 55 degrees if I use that normal distribution with a big variance. And so, okay, well, with that normal distribution, there's a whole lot of probability to the right of +4 and a whole lot of probability to the left of -4. And so when you simulate these things, you're going to get very small probabilities and very large probabilities and almost nothing in between that's noticeable in between. And so this is a silly prior. Now, if you had a lot of data, the data would wash out that prior, but there's only 23 observations here. And so, but in either case, I just hate the idea of putting a silly prior on something that doesn't make any sense, even though you're trying to be benign. So anyway, so possible alternatives: standardize the covariate T, place independent normal 0, 1 priors on the betas, and obtain the induced prior on the P55 and P75 again. I didn't mention, but the convergence for the previous prior is very queasy. I did it just for fun. I ran that model and I had a lot of trouble getting the program to even run. I was doing it in bugs. And when it did run, it took sometimes tens of thousands of iterations before I would have been comfortable with the convergence. So, well, anyway, what's the problem with that? If I go back to the original model here, I've got T varying between 50 and 80 some degrees. And I've got this huge prior on beta 2. And so this number is getting to be very large positive or very, very small negative a whole lot of the time. It just is creating all kinds of problems because of that. So anyway, so standardizing the betas. And so with standardizing, standardizing temperature gives me a number down here, comparably. This guy's between plus and minus 2, this guy's between plus and minus 2. So anyway, something that's a lot more tame than before. So here's the induced prior on P55, and then here's the induced prior on P75. So now if I play with the variance on the beta, right? I got a normal 0, 1. I could play with the variance, and I have. You can get these things to go. I can get this one to look like this one, and vice versa. And if I played with it long enough, I might be able to get them both to look uniform. Okay, well, why don't I just put a uniform prior on both in the first place? Well, of course, that's what you would do if you thought that was a reasonable thing here, where you really were ignorant. But anyway, I like to say good enough for government work. So, and anyway, so for more complicated situations, trying to put uniforms on these things is complicated. So here's a prior that we put on at the time. This is like over 30 years ago, roughly. And so the prior on P55, well, you think it's more likely to have at least one O-ring failure than if at 55 degrees than at 75 degrees. And so here, what I have is 2/3 of the probability to the right of 0.5 for P55 and 2/3 of the probability to the left of 0.5 for P75. Okay, well, these are rather diffuse. Notice I have a mode of 1 here and a mode of 0 here. And what I did was set up these constraints, being kind of mildly informative. And I picked the modes to be 1 and 0, and that gave me beta distributions like this. Okay, and now of course, I treated them independently. But of course, you could argue, well, of course, one of these has to be bigger than the other, usually. And you would expect one to be bigger than the other. But anyway, so you could easily incorporate that belief into the analysis and still treat these as, the prior is the product of these two densities. subject to this constraint, but it's not going to make any difference at all in this problem. And the convergence is vanilla. So, okay, so now I have these kind of real prior distributions. And okay, and I'm going to treat them independently. It's a conversation to have about that, but I'll leave that for now. And okay, so I have the relationship between the logits of the probabilities of at least one O-ring failure at these two temperatures and in an algebraic form here. And so this matrix gets called X tilde throughout. And well, anyway, I can easily solve for beta 1 and beta 2 either through high school algebra or taking the inverse of this matrix. So now, so I have a distribution on these guys over here. These guys are a function of those guys. I get an induced distribution. I can go ahead and do the Jacobian transformation thing and get the exact distribution on beta 1 and beta 2, or I can just do it by simulation, which is exactly how I do it. And an interesting note here is that suppose I had a probit regression instead of a logistic or a complementary log-log. Well, exactly the same procedure gives me a prior on beta regardless of what link function I'm using in the generalized linear model context. So I just change these logits to probits or complementary log-logs. So anyway, if I'm comparing two different models, I can have the same prior information going into the model specification regardless of the link. Okay, so here's some, well, it's kind of fun for me anyway. I guess I'll start with the mildly informative prior. We get estimates of 0.77 for the probability of at least one O-ring failure at 55 and 0.15 at 75. Notice that the mildly informative and the diffuse normal 0-1s with standardized time are very similar. So both with respect to intervals and point estimates. And then with the normal, with this very diffuse normal prior on the original scale, I get shrinkage up and shrinkage down, which of course is makes a whole lot of sense because of the induced prior on these guys basically said that's what's going to happen. So having a big influence. Okay, so this is when I was using what I called the mildly informative prior that involved the beta distributions, that's an example of what we call a conditional means prior from our papers back in the 90s. So the basic principle is that you have the expected value of y given x in vector form. So x is an n by p matrix of predictors. And well, that's the form of the expected value of y. It could be m, could be the identity, and so on for different generalized linear models. Okay, so we're going to specify a p by p. So p is the dimension of the regression vector. So we need we need to think about if we're going to put a full prior on beta, fully informative prior on beta, the full vector, we need a matrix x tilde and need a non-singular matrix x tilde and of hypothetical predictor values. These are predictor combinations that scientists can think about. And so we're going to consider m tilde to be the expected value of some hypothetical y's corresponding to those particular predictor combinations. And well, anyway, we put an informative prior on that m tilde. We're going to assume that the m tilde i's, the components, there's going to be p of them, yeah, are independent. So you can't specify vectors in the x tilde matrix or predictor combinations that are very close to one another, because otherwise then you're talking about almost the same kind of response. So they would of course be dependent. So at a minimum, you need the matrix x tilde to be non-singular, and then the choice of these components, these predictor values, is a major thing. And I'll talk about an explicit example here shortly. So if M is explicit, okay, and it isn't always, I'll give an example where it's not, but we'll solve for beta. And so we have an induced, we have a distribution on M tilde, that induces a distribution on beta. Well, anyway, so I think about something that I can think about means, particular predictor combinations, or at least I can find somebody, if I'm working with them in particular, that will be able to think about them, and take that information and put it onto this beta, which is not something that I can think about personally, especially in a nonlinear model. Okay, so anyway, so the partial, yeah, so partial conditional means prior. So details are in our book, but what? So nobody can put a real prior on 50 regression coefficients, even by this technique. We did it with 6, and it's hard work. We spent a whole day working on it with the expert in the situation. But so you could easily imagine putting a real, I call it a real prior, you know, it's something that involves subjective information from an expert. So it's anyway, okay. There's always a temptation to want to say a whole lot more, and I've got a lot more slides to go through. So anyway, so we partition the design matrix X tilde, we partition beta, and we imagine, to make life simpler for the moment anyway, that X12 tilde equals 0, which means that I would be able to you know, provide a scientifically relevant parameter that was a function of only beta 1 only. Okay, function of only beta 1. So, okay, it's, you know, it's not that hard to do this, even if this isn't 0, but it's a whole lot easier for me to talk about it. And so if I recommend you to our book in chapter 8, where this is, where we talk about this in great detail, if you're, you know, because it wouldn't always be possible to find a scientifically relevant parameter that only depended on beta 1. In other words, it might depend on both beta 1 and beta 2, in which case there's more complications involved with actually doing this specification. Okay, so anyway, but if you can do that, you obtain the induced CMP on beta 1, just like we were just talking about in the full case, and then put a reference prior of some sort on beta 2. So normal 0 with variance beta on these coefficients, and then look at the implications of that choice for different values of B on scientifically relevant parameters in your problem. Easier said than done, but it's work, but at the same time, that's what I do. That's what I like to do, what I think is a good thing to do. And yeah, all right, so here's an illustration, a substantive illustration of exactly that method of specifying a prior. So there's a subset of the full data set involving patients admitted to the University of New Mexico Trauma Center in those years, N is 300. So Ed worked with Dr. Osler while he was at the University of New Mexico. He was in charge of the emergency department there. So he is quoted by Ed. I don't remember this, but he reminded me that Dr. Osler believed that any well-calibrated emergency department doctor would be able to predict well the probability of survival or death after trauma surgery using available predictor information. So these are the predictors down below that he actually uses, you know, not in a formal sense probably, but he has that information going into trauma surgery. The injury severity, the scores range from 0 to 75. 75 is very, very, very injured. Revised trauma score, it's a measure of how sick you are, what your vital signs say, and so on. 7.84 is healthy, 0 is probably dead. Age, 10 to 60 in these data. Type of injury, blunt, meaning you get shot, or you fall off of a roof. Yeah, that's more like it. And penetrating, like you get shot or stabbed. Okay, so we used Dr. Osler's model, which is this logistic regression model. It has an age by type of injury interaction. And well, it means he believes that the effect of type of injury depends on age, and we'll see exactly that that's the case. So we're picking 6 covariate vectors that are relatively extreme within the data, so not too close together. We need to come up with a non-singular matrix X tilde, and we elicit information from Dr. Osler on these probabilities. And we use independent beta distributions for these guys after eliciting quantiles from the, for Dr. Osler's prior. And he, so Dr. Osler picked the levels that we would consider. And so the first thing we asked him was, what would be the easiest patient for you to think about? What kind of patient would be the easiest patient for you to think about? And so this is the X tilde corresponding to that patient. It's a patient that has a moderate injury, is perfectly healthy otherwise on vital signs, is 60 years old, which he calls kind of lacking reserve. And a 10-year-old has lots of reserve. So anyway, we all know what that means. But anyway, these are the combinations that he picked. He picked the first 4. We went sequentially, and we asked him at each stage, well, what's the next easiest patient to think about that's really different from that patient? And so we went through it one by one. And then we got to a certain point, and we were checking the non-singularity of the, or the linear independence of these vectors that we chose along the way. And we started having trouble. And he was having trouble picking the next one. And so we used some experimental design considerations to pick these last 2. And then he gave us information about the probability of dying under those conditions. Okay, and so these are his words. I took notes during our elicitation. We spent a whole day in a conference room, and it was actually rather enjoyable, but it tiresome by the end. And his words for the first probability: individual has good physiology, is not bad hurt, does not have a lot of reserve, and for whom there is added uncertainty due to age. And his best guess for the probability of dying was 0.09. And the second individual had bad physiology, very ill, young and resilient, not so badly hurt, but has a probability of 0.2 of dying because he's or she is more badly hurt, and so on through there. So here are the priors and the posteriors for the probabilities of death for each of these 6 types of individuals. And I would note that on the ones that we picked, where we picked the X tildes, his guesses weren't as good. His modes of his prior were not as consistent with the modes of the posteriors as they were for others. But in any case, this is our situation, and here are our inferences. So rather than talking about regression coefficients, which I hate, because all I know is if something is statistically significant or whatever, statistically important is the word I use in the Bayesian world. But that doesn't say very much. I want to know what it all means at the end of the day. So here is a figure where we're looking at age 60 in the left-hand column and age 10 in the right-hand column. And we're looking at somebody that is very sick in the top row and not as sick in the bottom row. And then we're looking at the probability of death as a function of injury severity. So if you look at a 60-year-old, the curve goes up very rapidly compared with the 10-year-old. So the 10-year-old has this reserve, so they're going to have an easier time surviving no matter what the injury severity is. And so anyway, so you can kind of compare left to right and up to down, and and in general, but anyway, the fun thing to look at for me is the penetrating versus blunt. And obviously the interaction has some kind of practical importance. So there's no difference in the inferences if you're older, whereas there's a noticeable difference if you're younger. This is not a statistically important difference, but I wouldn't want to exclude that from the analysis. I just have to write carefully about it. Okay, so the partial prior situation, again, I'm going to assume that I can isolate some parameters of scientific interest in just two, involving just two betas. Now, I'm going to standardize all my predictors that are continuous. I'm going to look at the baseline values for the dichotomous one. So I'm looking at a blunt. So here's my X tildes. So there's 6 of these. I've standardized predictors. So if I have 1, 0, 0, that means that all of these values are average injury severity, average RTS, revised trauma score, average age, and so on. And so this is going to make it possible for me to put an informative prior on beta 1, assuming I can get my guy to think about this situation. So he would know if we had this. We didn't do this at the time, obviously, but we would be talking to him about the average injury severity, which is a certain number. He'd have that in front of him. He'd have the average RTS in front of him. He'd have the average age in front of him. He'd be thinking about that situation. And this one is 1 standard deviation above the mean on the injury severity score, and we'd have that number sitting in front of him as well. But anyway, assuming I can get him to give us reasonable information under these circumstances, I can solve for beta 1 and beta 2 without taking an inverse. So anyway, and I can induce a prior on beta 1, a real, what I keep calling a real prior on beta 1 and beta 2. And I put something benign, hopefully benign, on the rest. Okay, so moving on to survival analysis. You know, I made the mistake of turning my phone off because I was afraid somebody might call me. I'm going to look at the time. Okay, I've got a little ways to go, but all right, survival analysis. One of my favorite things to do in my career. So this is so basically coming out of a paper that Ron and I wrote in Statistics in Medicine some time ago. Log of time given X is normal X beta sigma squared. Well, what's this? This is log normal survival model. Median of T given X is e to the X beta. Okay, so it's a median regression model. It's an accelerated failure time model. So what do I think about it when I'm putting a prior on something in a survival model or survival regression model? I think about median time to failure, or at least that's what I ask my expert to think about. So I pick some m tilde i's, e to the x I tilde beta. So I pick some x tilde betas that I hope my expert or I am able to think about. And so I get the relation log of m tilde is x tilde beta. I solve for beta. I've got an induced prior if I'm able to put a prior on the m tilde. Well, log normal prior for that is easy because I can take a best guess M0I for the median survival time for an individual with covariate x tilde I and a 95th percentile that I'm going to call gamma 0I, and I set AI to the log of M0I, and so that gives me the relationship between M0I and this prior that I put on the logs. And then I can go down here and solve for BI, so the variance on the log scale. I can solve for the BI because I already have a guess for AI and I have a guess for this 95th percentile. So anyway, things I can think about help me to induce a prior on things that are much harder to think about, namely the regression coefficients. And then, okay, so sigma, well, this is a little harder, but not much. it can be a lot harder depending on how far you want to go with it. So what I like to do is think about the 90th percentile. So, well, that's the formula for it in this log normal regression model. So what's the time at which 90% of the people involved in the population that I'm studying will have gone? So there's only 10% left at this point. I believe this is something that a doctor that can think about that's involved with these kinds of data. So anyway, then you see that it's just equal to m tilde times that. Well, I already have a guess for m tilde from what I was just talking about for a particular x tilde. Well, we're assuming a homogeneous error structure, which we could argue about, of course, but if we do that, the elicitation would not depend on a particular x tilde, so I can pick an x tilde that's convenient to think about and take that x tilde to get a guess for m tilde. And then I'll have a best guess for this 90th percentile. And I'll set that best guess equal to this and solve for a best guess for sigma 0. So now, of course, there's the issues of, if I would want to try more than one x tilde, I'd want to see if I came up with a sigma 0 that was similar in all those situations. If I didn't, I'd have to worry about things. But anyway, those are the kinds of things you'd want to think about when you're doing this. But anyway, it's kind of a relatively easy way to get a handle on sigma 0. So then the next step, well, uncertainty in sigma. Okay, well, there's an easy way and a hard way. I'm going to go through the easy way here. So suppose I was 100% certain that the 90th percentile of this survival distribution was less than or equal to some u tilde. So now I could pick this to be 100 years and I'd probably be safe if I'm talking about people. And anyway, and so then if 100 years sounds too big, well, you can pick a smaller value until you're kind of okay with thinking, well, it just really can't be bigger than that particular value. So then if I assume beta is independent of sigma, I'm 100% sure that this 90th percentile is less than or equal to that, given my guess for the median failure time for this particular type of individual. And elementary stat 7 in UCI calculation gives me an upper bound on sigma, uniform on that. And if you don't like the value, make it bigger, but don't make it 400 years if if you're talking about people. It's silly nonsense. Okay, so another one of my favorite things in the world, statistical world, has been Bayesian nonparametrics. So I just have 2 slides on this. And 31, okay. So anyway, so Tim Hansen and I worked on mixtures of, Tim Hansen really did most of this. He did a great thesis, and then at the end, he sort of said, well, what about mixtures of finite polyetries? and so he dove in and went crazy for quite a long time and really laid this stuff out in a nice way. But so here the idea is, instead of having a log normal regression, instead of putting a normal distribution on the errors here, you put a mixture of finite polyetries. Well, okay, so that's a whole topic in itself, just almost to tell you exactly what that is. But basically, it's a non-parametric, you're putting a non-parametric prior on the error distribution. And so these things, and we're centering that non-parametric prior on a normal distribution with mean 0, and you can set this up so that it will have mean 0. So it's a mean 0 non-parametric distribution that varies around the normal distribution, okay? So you get flexibility. So it's a semi-parametric model that has great flexibility and it's still a median regression problem, you put the same prior on that we did for the log normal model. Okay, you can embed a family of log normal distributions as essentially the prior guess in this setting that allows for much greater flexibility. This C is something you can choose or put a prior on to make it more or less flexible. And the J means you have to truncate it. You have to make it finite. The real mixture of polya trees is infinite, so it has to be truncated. Okay, and then another one that I like too involves well, here in this case, I'm just talking about a Dirichlet process mixture of log normal models. And okay, this is more complicated. It's harder to put a prior on. Everybody has their own way of doing this now. There may be ways that I don't know about yet because I haven't actually been doing the programming ever. So it was always my students that were doing that. But the issue is, this is something that I wanted to know how to do for a long time, how to put the kind of prior I'm talking about into this situation. I'm working on it at the moment on a paper that involves cow data, and I've actually I've specified what I call a real prior that involves the biology in this situation. But anyway, I recommend you to this one paper that I know about by my friend Prakash and his co-authors that he's quite proud of and thinks is a really good thing. And I know there's others. I'm sorry for not mentioning or for doing the hard work to find them all. But anyway, it's a one slide thing that, anyways, just one of my loves. So there it is. Okay, so now the next problem is, I need to look at the time again. Okay, coming close to the end. Yeah, I can do this in one slide. So this is a nonlinear model. So there's a semicolon here. Okay, so we've got independent normals with a nonlinear structure in the covariate. And Carlin and Gelfand analyzed this data set that I'm sure has been analyzed a million times by others. It's a growth study on length Y and age X for 27 dugongs, which sounds Australian to me, but I don't know. I should have looked it up. A large marine mammal. And they used this model in their analysis, this nonlinear model. And so, well, anyway, this is a situation where I can have my expert think about the means, the mean response, okay, with not thinking about this yet, but thinking about these means, whatever they are, and place independent normal distributions on a selection of X tildes. And in this case, since it's a scalar, so it's not a matrix, it's a vector, and I'm looking at standardized age. And so I've got the mean response, one standard deviation above and one standard deviation below. So anyway, okay, so what am I going to do? So I've got my specification of my prior. What am I going to do? Well, what do you do when you have a nonlinear model that you want to make simpler? Well, you linearize it. So I take a Taylor approximation, a first order Taylor approximation, that gets me linear in beta. So then I can solve for beta in terms of M tilde in terms of the approximation. So that induces a prior on beta in this situation. So that's what that's all about. And then my last topic, so suppose I have, so this is, my headers are all covered up by the stuff that's usually at the bottom. So this is a Bayes factor problem. So issue of putting priors on when you're constructing Bayes factors. And so we have different models with different probability distributions under those models. So for example, if you wanted to compare the log normal and the Weibull for non-negative data, you'd have regression coefficients in both situations. So we need to elicit priors for the two different types of parameters. But if this is the situation I'm in, I can do the conditional means prior in both cases with different links. So I'm putting the same prior information in so that when I make the comparison of the models, the priors are comparable. In fact, they're the same. Well, they have the same information. All right, so we need marginal predictive densities. Well, that's just, we've seen this before, and it's been called a likelihood. Lindley called it a likelihood. But anyway, to me, it's a marginal predictive, where you integrate this guy, the sampling distribution under that model against the prior that's involved there. And you do it for both of them. The base factor is the ratio of those guys. And if the base factor is big, you like model 1. If it's small, you like model 0. Okay. Okay, so now this is the classic model in statistics: independent samples, different means, common variance, the standard T statistic. Okay, reparameterize the model so that delta is the difference in the means divided by sigma. That's called the effect size in the psychology literature and elsewhere. And then we need a one-to-one transformation. The nuisance parameter gamma is the average of the means, and put a diffuse reference prior on gamma and sigma squared, leaving you with placing a real prior on delta, on the effect size. Okay, so normal with mean lambda and variance sigma squared delta, and we want to compare the model 0, delta equals 0, so the effect size is 0 and or not. All right, and so in this American statistician paper, Peter and his students and I, Peter Westphal and his students and I derived the Bayes factor. It's a function of T squared. There's a whole lot of Bayes factors, just prior distributions under these circumstances that are only functions of T squared. So there's a bunch of literature on it. No time to go into that. So let's talk about a real problem. So my partner, Jessica Utz, is one of the world's experts in helping psychologists that study psychic phenomena to do their statistics right. So anyway, so she pulled me into this. So she has a good friend named Daryl Bem, who is a well-known psychologist who published a paper called Feeling the Future. Okay, and the idea was whether people that are sitting at a computer wired up with stuff to measure their responses, their physiological responses, whether and so the computer's designed to show, well, it's like showing white noise, and then it's going to show either a shocking picture or a benign picture. And the question is whether the autonomic response for the shocking pictures would be different than the one for the benign pictures, and the answer was yes, according to very small p-values. Okay, so anyway, so then for reasons I'll come to later on the next slide. So Daryl asked Jessica, who asked me, to help reanalyze the data as a Bayesian. Okay, and so we're going to use a real prior. So background information is that the effect sizes in previous meta-analyses ranged around 0.18, and in other meta-analyses of effect sizes in this area of PSI, around 0.28. So these are kind of small, okay, I guess. Anyway, so they asserted that no reasonable observer would ever expect a delta bigger than 0.8 in laboratory psi experiments. So we put a prior on here that has a 95% probability on delta, that has 95% probability that's less than 0.5. Okay, so in Jessica's elementary stat book, she points out that the effect size for the difference in adult male and female heights in the US is 2. So this is obviously something that we all can observe, that we don't need a statistical experiment to prove that women are not as, on average, not as tall as men. Okay, so it seems in general reasonable to assume that maybe studies of all kinds would have a delta less than 2. So maybe you want to pick a bit larger value, depends. Okay, so the reason we were writing this follow-up paper with a Bayesian version is because others, Wagemakers et al., used our Bayes factor with a different kind of prior. Well, instead of a normal prior, it's not ours, it's the world's, and others have been doing this long before us. But so anyway, they used a Cauchy prior, which is it's one that's been there. And Jeffries, I think, was the first one to introduce it. So they published a paper basically saying, well, you really ought to be doing a Bayesian approach, and you're going to get a different answer if you do that, and it won't be the one that you like. But anyway, so my point here is that these are the prior probabilities with a Cauchy prior, that the effect size in absolute value is bigger than 0.8, 0.57, bigger than 2, 0.3, bigger than 5, 0.16. So these are extraordinarily large prior probabilities for delta that, in my mind, ought to be regarded as less than 2, can be really large. Okay, so so if the effect sizes were that large, there'd be no debate about the reality of psi. And there's obviously a huge debate about it. All right, so we got the Bayes factor using all 9 experiments from the study, using the Cauchy prior. Bayes factor is 0.632, while using our prior, it's 13,699. Priors matter. Priors matter. And people will still debate, depending on what their prior beliefs, real prior beliefs are. But I don't think
sorry, Wes, for interrupting. The organizers are very strict and are going to terminate the session in 2 minutes.
Oh,
so,
okay.
Yeah. So
I'll just say that this is a worse prior, okay? And this is what I said all along the way. There's the probability of at least one O-ring failure at 32 degrees. It's very high. And there's the dugong thing. So I'm done. Sorry to have gone over.
So maybe, so first of all, many thanks for the great talk, and you're getting some real applause here. Thank you. And we do have a number of questions. Let me just read the question by Ed George. So he's saying, great talk, Wes. On his question is following, for the calibration of priors or regression coefficients, suppose your expert provides prediction at many more points than there are parameters in the model. How would you handle that? I think that's a great question.
Yeah, so we actually got that question from a referee, so he might have been a referee. And I don't remember off the top exactly how he responded, but it is a great question. And so I guess I might try subsets of the values and see what I came up with, rolling across different subsets of the whole set, and see if what kind of consistency there was or wasn't. In other words, if I was coming up with similar prior on the things that the expert was thinking about, if they were coming up different, I'd want to go back and redo the elicitation. So I would want to challenge the expert based on showing them how things were coming out differently depending upon the particular elicitation, and try to come to some kind of resolution about it. So, in one situation I was in, things really looked funny after the elicitation. And then my guy said, oh, I was really misthinking something. And so he was able to square it away in his head now. So I don't know exactly what the something was, but anyway, when it was redone, it really did make sense. So, but it's a back and forth. You know,
Yeah.
it's got to be a back and forth.
So many thanks. I feel like the organizers are going to terminate any minute. So maybe let me read the very final comment. I mean, there are a lot of comments. Let me just read one of them. Fine talk and an exemplar for the ISBA Distinguished Series on Bayesian Foundations. And I think that's a great conclusion of the session. So many thanks to Wes, and many thanks to all who participated. And let's give Wes a final hand for this wonderful presentation.
Thank you very much. It was a pleasure.
We will see when we're going to be terminated. But I think they will just finish. Yeah. So, I mean, I can continue reading the questions to you, but I think they're not going to be recorded anymore. And we do have some audience here. So, do you think priors in survival analysis should take into account the censoring rate? This is, should one use different priors in cases where the censoring rate is 10% versus 60%? Or should one use the same prior regardless of the censoring?